Welcome back to our series on alkyne reactions. In this video, we shift our focus to halogenation, the addition of halogens like Br₂ across the CC triple bond. Since alkynes have two pi bonds, they can react once to form a dihalide alkene, or twice to form a tetrahalide alkane. Our focus here is the addition of excess Br₂ to the terminal alkyne, propyne, dissolved in CH2Cl₂. Starting with propyne and one equivalent of Br₂, the first addition yields a dihalide alkene. This reaction shows anti-selectivity, meaning the two bromine atoms add to opposite faces of the triple bond, forming a trans or E product, E₁,2-dibromopropane. When the remaining pi bond reacts with the second equivalent of Br₂, a second anti-addition occurs across the double bond. The final product is a tetrahalide alkane, 1,1,2,2-tetrabromopropane. The overall mechanism for alkyne halogenation closely resembles that of alkene halogenation. However, the reactivity changes significantly after the first addition due to the electronic effects of the attached halogen atoms. Stage 1. Formation of dihalide alkene. Step 1. Bromonium ion formation. The bromine-bromine bond is polarized as the electron-rich pi bond of the alkyne attacks one of the bromine atoms. The resulting structure is a three-membered ring intermediate known as a bromonium ion. This is an effective way to minimize the formation of a highly unstable vinyl cation, that is, an sp hybridized carbocation, promoting anti-selectivity. Step 2. Nucleophilic attack. The bromide ion then attacks the more substituted carbon of the strained bromonium ion ring. This preferential attack on C2 is due to the neighboring methyl group slightly stabilizing the developing positive charge in the transition state. Since the attack is forced to occur from the side opposite the bridge bromine atom, the two bromine atoms are positioned trans to each other. The first stage product is the dihalide alkene, E₁,2-dibromopropane. Note that the rate of the alkyne's first addition is generally slower than that of an equivalent alkene. This is because the sp carbons of the alkyne hold electrons more tightly than the sp2 carbons of an alkene, resulting in lower pi electron availability. Stage 2. Formation of tetrahalide alkane. Step 3. Second bromonium ion formation. The resulting E₁,2-dibromopropane, now an alkene, reacts with the second equivalent of Br₂. This reaction is significantly slower than the first addition. The CC bond's pi electrons are less available for attack because the two existing Br atoms exert an inductive withdrawal effect. Despite this reduced nucleophilicity, the alkene eventually attacks Br₂, forming a second bridged bromonium ion intermediate. Step 4. Second nucleophilic attack. The second bromide ion attacks the bromonium ion intermediate from the side opposite the bridging bromine, as before. In the bridged intermediate, the more substituted carbon bears the greater partial positive character. So bromide preferentially performs a backside attack on C2 rather than C1. This electronic preference, partial charge stabilization, outweighs simple steric arguments, and the anti-opening of the bromonium ring delivers the final product, 1,1,2,2-tetrabromopropane. Let's summarize. Stage 1. Formation of dihalide alkene. Step 1. The alkyne attacks Br₂ to form a bridged bromonium ion. Step 2. Bromide attacks the more substituted carbon from the backside, yielding E₁,2-dibromopropane. Stage 2. Formation of tetrahalide alkane. Step 3. The double bond, slowed by the negative inductive effect of the existing bromines, forms a second bromonium ion. Step 4. The final bromide attacks, yielding 1,1,2,2 tetrabromopropane. Let's organize by keywords. Anti-addition ensures the two halogen atoms are positioned trans to each other across the multiple bond, resulting from backside attack. The bromonium ion is a cyclic, three-membered intermediate that bypasses the unstable vinyl cation and dictates the stereochemistry. Dihalide alkene is the intermediate formed after the first Br₂ addition, and tetrahalide alkane is the final product formed after the second Br₂ addition. To wrap up, those who wish to deepen their understanding of alkyne halogenation and its related reactions are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.